Hello and welcome. In this short module, we will review some concepts of signals and representation that is necessary for us to further study digital communications or rather digital optical communications. To begin with, let me start by claiming that we consider signals, which when I say signal, you think of a waveform which would be depending on time and it would be changing with time, such as S of t for example. We consider these signals as vectors. To back up what I am saying, because the notion of a signal as a vector is very important in communication systems, because it allows us to think of signals which are some continuous functions of time, which we assume them to be some continuous functions of time, in terms of vectors which are having certain geometrical properties. So, it is a way of geometrically understanding what signals are that allows us to further analyze digital communication systems, and therefore, a brief review of those ideas with which we associate or we identify signals with vectors is something that we are going to do now. To start with, let us first briefly recapitulate a few factors or few facts that go with vectors, right. So, when we say a vector, the immediate thing that would come to our mind is physical quantity such as velocity, and this velocity is a quantity that has both magnitude, right. So, we say that the car is moving along a particular direction at 60 km per hour. So, that would be the magnitude part of it, and the direction, whether it is moving from Kanyakumari to Delhi, in which case we can think of the movement from south to north, or you can think of any other directional movement. The direction part is the direction property of the vector. So, we say that a quantity is called a vector when it has both magnitude and direction. Quantities that can only be specified or that can be specified with only magnitude, such as temperature at a particular point, is called a scalar. So, this is a vector. If you just have a magnitude, for example, speed of the car, it would be 60 km per hour. So, when you specify speed, you do not normally specify the direction. However, when you specify velocity, you specify both its magnitude as well as its direction. Now, this is something that is quite elementary in our thinking of vectors, but we also have other representations of this vector, right. So, one geometric way of representing a vector is to draw an arrow. There is a head of the arrow and the tail of the arrow, and we are taught that the length of this arrow, which would be this particular distance between head and tail, is called the magnitude of the vector or the length of the vector. So, we can have a graphical or a visual representation of a vector in which we specify the head of the vector and the tail of the vector, and the distance between these two, the 2 points or the length of the vector, would be called as the length of the vector. Now, we can give a name for our vector. For example, since we have talked about velocity as one of the vectors, we call this vector as V. To distinguish between a scalar and a vector, you put a bar or an arrow sometimes. In print, you would write V in terms of its boldface print. Okay. So, just to distinguish that from the scalar. So, I will be using this bar, the overhead, on a quantity, which then would mean a vector. Okay. So, this vector which I have graphed here as a particular direction, and it also has its length. The vector is given by V with a bar over that would be the way in which I will name this vector. Then I can specify the length of the vector, or I will use a special symbol to specify the length of the vector by enclosing that vector between these two lines. Okay. In a more technical language, this particular quantity which we have written is called as the norm of the vector, and you will see soon that sometimes instead of norm, it is a norm squared that becomes important. So, you can think of norm as essentially length, unless we really want to go very technical into all these aspects, which we are not going to. So, this is a vector V with a bar there, and the length of the vector is represented by this particular quantity. Okay, that is what we call as the norm. Now, when you have two vectors, let us say this is a vector V and then I have a vector U, right. You can see that there is some sort of a graphical relationship between the two, right. So, you can see that there seems to be the way in which these two vectors v and u are written, there is a specific angle between the two, although you would not be able to find that out so easily. In order to find the angle between the two vectors and in order to even find the intuition behind that one, you have to understand that mathematically a vector u or a vector v can be slid parallelly, okay, and in this particular direction, as long as I am not changing the length of the vector. So, as long as the length of the vector is unchanged, you can slide it parallelly and then up and down. So, when you do that, you are not changing, well, you are actually changing the physical vector. If for example, this represented a car going in this direction, then moving u parallelly so as to form, let us say, let me use a different one. So, this would be the vector u that has been moved, right, that would be the vector that has been moved. These two vectors would be completely different, because this would specify a car on this road, whereas the vector that is represented by this u moved would be a car in the same direction, but it would be on the parallel road or it would be on the other road. Physically they might be different, but mathematically they are identical. Therefore, we consider the vector u moved as equal to the vector u itself. Okay. So, this is something that you have to remember. You can also slide this vector up and down. Okay. So, you could have actually done that one right over here. You could have, for example, taken this vector and just slide it just under here, so that this would have become the new vector. Why am I doing all this? Because it simplifies my analysis, or it simplifies my understanding if we consider both vectors v and u to have a common origin O. Okay. So, if I bring two vectors which are spatially separated, but I can bring them such that their heads are intersecting at a particular point, which is the common origin point, then I can talk about the angle between the two vectors. Okay. So, I can measure the angle either from the vector v or from the vector u, and I denote this angle by theta. If theta is equal to 0 degrees, right, then we know that the vector v and the vector u must be in the same direction, only then the angle is 0. If theta is equal to 180 degrees, then I know that the vector v must be opposite in direction to the vector u, correct. What happens when theta is equal to 90 degrees? Then we have what is called as the perpendicular case, or the vectors are said to be perpendicular to each other. Another name for this is orthogonal to each other, or in other words, vector v will be orthogonal to vector u when the angle between the two is equal to 0. Of course, in the way I have written, I have put the head of the vector u onto the tail of the vector v. I could equivalently move this vector u, right, parallelly and then write it in this way. So, these two vectors, as I said earlier, they are equal to each other. So, the angle between these two, which defines the perpendicular thing, is 90 degrees. So, the angle between these two lines or these two vectors is essentially 90 degrees. Associated with this, there is one other concept that is very important. We ask this following question: suppose I have a vector v and in general I have a vector u. Now, I have a common origin to both of these vectors, which I am denoting by O. If I ask what is the amount of u contained in v, this seems to be a slightly strange question to ask as to how can one vector be contained in another vector. For a full answer, you have to wait for a theory known as vector space, but the short answer is that if I were to consider dropping a perpendicular from u to v, then I see that this particular length would represent the amount of u contained along v. Okay. In earlier classes, you might be more familiar with this word called decomposing a vector. When you decompose a vector, what you would have done is you would have taken the vector u and decomposed it along this particular horizontal vector and the vertical vector, and in this case the horizontal vector is the vector v, and this length that you have obtained, which is shown in this orange color, would be the component of u along v. Okay. How do I obtain that length? Suppose the angle between the two is theta, then you define what is called as the dot product of the two vectors. This is one notation for the dot product. You might be more familiar with this notation, which is u dot v. This notation is also sometimes used, okay, with a comma instead of a length L. These are typically also, these are actually also called as inner products, okay, and this is the notation that is typically used in quantum mechanics, and this is the notation that is sometimes used by mathematicians, and this is the notation that we normally use this notation. So, you can pick any of the notations. Let me pick arbitrarily this particular notation. Okay. So, I will pick this notation because I am kind of used to this. This will denote my inner product. The physical meaning of inner product is that it gives you the length of the vector u contained in V, and to obtain that length you have to take this vector u, drop a perpendicular. This is perpendicular because if I were to denote this vector by say E, then I know that the angle between E and V is equal to 90 degrees. So, if I drop this perpendicular E and then I have find this distance which is given by this orange color, then I will obtain the inner product. Okay. Mathematically, the inner product is given as the length of the vector u multiplied by the length of the vector v. There is a simple multiplication between the two, and then there is also multiplication, this is also multiplied by a factor cos theta. In fact, this cos theta is equal to 0, then it implies that theta is equal to pi by 2, in which case the vector u will be perpendicular to vector v. So, if you were to look at the component of the vector u onto the vector v, you would find that that component is actually 0, right. So, this is the notion of inner product, or called as dot product, or sometimes called as the scalar product of two vectors. Interestingly, what would be the scalar product of the vector v with itself? Well, I have the vector v here. If I project the vector v onto itself, what I get would be this length square. Why do I get a length square? Because mathematically expanding this v on v itself is to obtain the length v. I have to write it twice because there is u and v, here it is v and v, and the angle theta will be 0, therefore cos theta will be equal to 1, and we know that this portion is length of v, this is length of v. So, what I get is the length of the vector square, and this quantity would always be greater than or equal to 0. When will this be equal to 0? When there is a special vector known as the 0 vector or the null vector is involved. Otherwise, this magnitude would always be greater than 0. It can have any magnitude, but amongst any magnitude, one particular vector is important. This vector is called as the unit vector. The unit vector has a magnitude of 1, okay, and it has a direction somewhere. This direction of the unit vector is denoted by the subscript along which it is supposed to be directed. The cap is to denote a unit vector, and the subscript v which we have written will tell us that the vector is directed along v. Okay. What do we mean by that? Well, consider this vector v here. The unit vector along this direction would be a vector which has a magnitude of 1 and it is directed along the vector v. So, this particular vector which we have written in the orange is the vector hat av. So, this would be the unit vector along v. So, how do I obtain the unit vector? All I have to do is take the original vector v and then divide by that vector's length, right. So, if I divide the vector v by its length, then I would have normalized the vector v with its length, then I would obtain the unit vector. Again, I kind of seem to be missing that a hat part here. So, this would actually be a hat along vector v. When the two vectors v and u are perpendicular, the corresponding unit vectors, which is a v, right, and this vector a u, they are also perpendicular to each other. So, the unit vectors along the direction of the original two vectors which are perpendicular will also themselves be perpendicular. Notice that I have not actually talked anything about the coordinate system. These vectors could be vectors in Cartesian coordinate system, which is described by xyz axis and the unit vectors x hat, y hat and z hat, or they could be cylindrical coordinate system, vectors in cylindrical coordinate system, in which case the vectors would be having unit vectors r hat, phi hat and z hat. They could be spherical coordinate system, you get the point, right. They could be vectors in any coordinate system. What we have talked about are the geometrical properties of these vectors which must hold in every coordinate system. Why do we normally introduce a coordinate system? Because it will make our life simple to understand and to manipulate these vectors. You can't always go back and keep drawing the geometry. So, what you do is you introduce a little bit of algebra. So, geometry is the original vector directions, how they are geometrically related, whether they are perpendicular, whether they are apart 45 degrees. These are the quantities which are geometrical, and if you start giving them numbers and manipulate those numbers, then you have come down to a particular coordinate system. Okay. In a particular coordinate system, I can express any vector. For example, I take the Cartesian coordinate system. This is the so called rectangular Cartesian coordinate system, which is described by 3 unit vectors in the so called 3-dimensional space. It is described by 3 unit vectors which are labeled as Ax hat, Ay hat and Az hat, and any vector v can be written as some component of the vector along x plus some component of the vector along y plus some component of the vector along z. Now, if I assume that this vector is only along the x direction, then I know that by simply flipping this equation, I know that what I have written implies that the vector v will have a direction or will have a magnitude of Vx, and it would be directed along Ax. If I assume that Vx is 0 and Vz is 0, which means that my vector is actually directed along the y axis, then Vy will give you the length of the vector v. Okay. In general, if I have a vector in the 2 unit vectors in the 2-dimensional space, which is described by Ax hat and Ay hat, any vector here can be broken down into 2 vectors which are themselves perpendicular to each other. This component is Vx and this component is Vy. So, the corresponding vectors along these directions is given by Vx Ax hat, and this vector is given by Vy y hat Ay hat. Okay. What we have also done is to introduce, without telling you, that if I want to add 2 vectors geometrically, so call this as vector v and the vector u. If I want to add these 2 vectors geometrically, what I would do is to put one vector, say u, on the tail of the other vector. Okay. So, if I put like this, and then the resulting vector, which would be the sum of these 2, is given by the third vector, which is directed from the head of one vector to the tail of the other vector. So, this vector which I have written will give me the sum of these 2 vectors. So, if you go back to this particular vector which we have written v here, you can immediately see that this would be equal to the vector along x, which is given by Vx x hat, this vector, and the vector along y, which is given by Vy Ay hat. If I add these 2 vectors, I get the original vector v. Of course, I can continue to do this one for the case of n dimensional, although it is very hard to imagine those n dimensional spaces. Mathematically, I can represent any vector v by giving the components of v along that particular unit vector. So, let us say if I have n unit vectors which are labeled as a1, a2, a3 and so on, then finding out the components of the vector v along each of those unit vectors, I can sum those corresponding vectors, not the components, sum the corresponding vectors in order to reconstruct my original vector v. Okay. I can think of this vector v in the n dimensional space as being composed of n vectors which are all perpendicular to each other, because we assume that this set ai hat of the unit vectors I is equal to 1 to n are themselves perpendicular or mutually perpendicular. What we mean is that if I take 2 vectors ai and aj, they can be 2 different, I must not be equal to j, then this fellow will be equal to 0, because they are perpendicular to each other. If they are equal, then they would be equal to the value 1, that is, this would be when I is not equal to j, this would be the case when I is equal to j. Okay. And writing a vector in terms of its components, component vectors, is called decomposing a vector. Decompose a vector into its components. Okay. So, I hope that these concepts are very clear. This was just a brief review. Now, what we will do is we want to think of a similar things for the signal. So, let us start by looking at it. Suppose I have a signal which is a waveform, a continuous function of time s of t. Okay. So, this waveform which I have, let me assume that this lasts or this is defined over a time interval 0 to t. Okay. I have considering this one to be a t second signal, in the sense that over that particular time t, this signal s of t is described. Okay. It can have any shape. Okay. It could be, for example, this one between 0 to t, or you can have a vector which is, say, this case. All of these are assumed to be continuous and bounded. These additional constraints are just so that the mathematical operations remain finite and they do not run off to infinity, in which case it would be difficult to work with those. So, I am introducing these additional constraints for that. I am introducing the constraint of the t seconds, because in digital communication systems, every second the source would send out a new waveform. Okay. That would presumably contain some amount of information. So, it contains information and it lasts t seconds. Okay. So, for that reason I consider a set of such waveforms. So, let me label the set of waveforms as S1t, S2t and so on up to, say, SMT. Okay. So, this is my set of vectors which all can be different, but they have all been defined over the same time interval 0 to t. Now, these vectors are, they are just some waveforms actually. I am sorry, these are not vectors. At this point they are not vectors. These are some waveforms which are functions of time. Now, how do I claim that they can be vectors? If I have to claim them as vectors, or if I have to claim that signals can be treated as vectors, then I have to find couple of analogous points. First, I have to find a unit signal. Okay. I have to, first of all, even before finding unit vector or along with finding vector, I have to define inner product of two waveforms, although this terminology is not used. So, let me put them in quotes. My idea is that I replace whatever that was there with vectors in terms of these signals. So, I have to find a unit signal which would capture this particular equation. It would capture this equation, right. I can take the original vector v, divide by its length. So, I clearly have to define length as well, and I already know that length is related to the inner product of the two vectors. So, in fact, inner product length can be defined together. So, I need something that would correspond to the length as well, and I need an ability to decompose signals into its component waveforms, or decompose these waveforms into its component waveforms. So, let us tackle all these issues with signals and then see that if we define the inner product, I am not relying on anything, because there is no geometric intuition to the signals S1, S2 and so on up to Sm at this point. So, I have to come up with a geometrical intuition. I do that by first defining the inner product of the two waveforms S1 of t and S2 of t, assuming that these two are real signals. It is very easy to just consider what would happen when they are complex signals, but let me just give it for both. Okay. I will do it one, the others can be easily obtained. Okay. So, the inner product of two vectors is given by, if assuming that they both are real, they are given by this particular integral. Okay. If S1 and S2 are complex, then the inner product is given by S1 S2 complex conjugate dt integrated over the same time interval 0 to t. Would this inner product make sense? Yes. When you have S1 of t is equal to S2 of t, then this quantity 0 to t S1 of t mod square, or rather square dt if S1 of t is real, or it would be S1 of t magnitude square when S1 of t is complex. These two quantities would be greater than 0. Why? Because the integrand here is greater than 0. So, therefore, the integral will also be greater than 0. So, here I have the notion that inner product of a vector with itself must always be positive. When will this be equal to 0? This will be equal to 0 only when S1 of t is defined as 0 for all time t. So, this is a small mathematical symbol to indicate that this is for all. So, for all time t, if I define this S1 of t is equal to 0 or in general any signal to be equal to 0, then the inner product of that 0 signal will always be equal to 0, right. We also define that two waveforms S1 of t and S2 of t are orthogonal to each other. These are orthogonal to each other when their inner product, which is this particular integral vanishes, right. So, when this integral results in 0, then we call them as orthogonal to each other. So, what we have seen is that this particular definition of inner product, right, has allowed us to capture some of the geometrical aspects like inner product and length, perpendicularity or orthogonality. It has also allowed now us to define the unit signal. Why? If I want to find the unit signal along S1, so let me denote that one as phi S1, and this of course has to be a function of time t, and because this is a unit signal, let me put down a hat over this. So, if I want to find this, I want to take this signal S1 of t and divide that signal by its length, right. What would be that signal S1 of t? Well, if I know that the inner product of these two vectors, that is, if I know that the inner product of the waveform S1 with itself actually gives me the length square, right, this is the norm square. Therefore, inverting this relationship, I obtain the length of the signal S1 of t as square root of S1 of t with S1 of t itself. So, square root of S1 of t with S1 of t itself will give me the length. So, I can put this length here, okay, into this expression. So, length from equation 1 I can put down into equation 2 in the denominator and obtain this unit signal phi S1. Okay. As an example, consider this signal which is cos 2 pi fst and another signal sin 2 pi fst. Call this one as S1 of t, call this as S2 of t. Okay. Let us find out what would be the length of this signal S1 of t, which is obtained as the square root of S1 of t inner product with itself, right. So, I obviously have to evaluate this argument inside the square root, and that argument is basically 0 to t, and this would be cos square 2 pi fst dt. I know that cos square theta can be written as 1 plus cos 2 theta divided by 2, and then that cos will integrate away to 0, because I am assuming that fs into t is much larger than 1, or if you are not happy with that, I can consider fs to be some integer multiple of 1 by t. Okay. So, it must be some integer multiple, or it must be very large compared to 1, so that all these high frequency oscillations are all gone, and what I get with this one is basically t by 2. So, what I have obtained is just the inner product. So, what I have obtained is the inner product, but the length would be, if I want to find the length, I have to take the square root of the inner product. So, I get square root of t by 2. Therefore, the signal phi S1 of t, which is the unit signal, okay, this is a unit signal, okay, is given by the original signal S1 of t divided by square root of t by 2, which I can rearrange and write square root of 2 by t cos 2 pi fst. Similarly, you can show that phi S2 of t can also be written as square root of 2 by t sin 2 pi fst. Now, if you were to find out whether this phi S1 of t is really perpendicular, this is a shorthand notation, to phi S2 of t, perpendicular orthogonal. So, if you want to find out whether these two are orthogonal to each other, you simply have to consider the inner product of these two itself, right. When I consider the inner product, this square root of 2 by t would be common to both terms, it would come out. So, it becomes 2 by t 0 to t, then I have cos 2 pi fst sin 2 pi fst dt. Clearly, cos signal would be over the time duration 0 to t, it would be function of this form, whereas the sine function would be, so I hope I have not written it improperly, but if you look at the sine function, what this implies is to basically take the area under the product of these two, and that area actually vanishes out, because one of them is OR function, the other one is even function. So, this fellow will be equal to 0, indicating that originally S1 of t and S2 of t are orthogonal. Okay. And one other concept is to look at the decomposing the signal into its components, because the corresponding relation is that if I have a vector v and if I have, for example, a 3D space, then it is possible for me to define 3 vectors which are mutually perpendicular to each other, and in terms of those vectors I can define, in terms of those unit vectors, say Ax hat, I can define this, right. So, let me consider only 2 such particular cases. So, Vx Ax hat plus Vy Ay hat, I can define this vector v. Similarly, if I want to write down the vector in general, let us say g of t, then what I have to do is I have to find out the inner product of this vector g of t onto the unit vector or the unit signal phi s1 of t. This would give me the component of g of t on phi s1 of t, and then this has to be multiplied along the unit vector in the direction of x, right. So, if you go back to this one, this Vx is nothing but the inner product of v with Ax hat. Why is that so? Well, this is because if I now look at the length of this vector, go back to the definition, the length of the vector v, Ax magnitude or the length of this one, and cos of theta, where theta would be the angle between this v and Ax hat, right. This length is 1, this length is v. So, what I get is v cos theta, and this is actually the length of the vector v along x direction, but this is just the length. If I want to find out the vector along x, I have to multiply this one by the unit vector Ax, right. So, looking at the same logic here, take this g of t and then find the inner product of g of t onto phi s1 of t. We call this as the projection. So, we say that project g of t onto phi s1 of t. This will give you the length of g on phi s1, multiply this one with phi s1 of t, and similarly you can multiply this, find the inner product of g of t with phi s2 of t, right, and then multiply this resulting component by phi s2 of t. This way any signal s of t which satisfies certain conditions can be written in terms of these 2 vectors which are the unit vectors or the unit signals. So, in a sense we think of a signal as a vector. Much more important discussion would be possible when we discuss the optimum receivers. At this point it is perhaps enough for me to discuss this relation or the notion as a signal as a vector, because that is all I need. I will be considering next the amplitude shift keying, phase shift keying, in general an M-Array phase shift keying, or I will be considering QAM. All these modulation methods can be geometrically understood by talking about 2 unit signals, okay, or 2 orthogonal signals. These orthogonal signals are cos 2 pi fst and sin 2 pi fst. The corresponding signals which are the unit signals along these 2 can be labeled as phi s1 and phi s2 of t. This is enough for me, because we saw in the last module that any signal s of t can be described by its in phase component si of t cos 2 pi fst minus sq of t sin 2 pi fst. As long as si of t and sq of t are nearly constants, okay, over the time duration 0 to t, then we know that cos 2 pi fct and sin 2 pi fct are essentially perpendicular to each other, right. So, this fellow is actually given by, I know that phi s1 of t is given by square root of 2 by t cos 2 pi fst. So, I can in fact write cos 2 pi fst as t by 2 under root phi s1 of t. Okay. So, when I have si of t and sq of t, the in phase and quadrature components as constants, right, over the duration 0 to 2 are approximately constant, then this particular signal s of t is actually a vector in 2 dimensions. In this case the dimensions are coming from phi s1 and phi s2, which are related to cosine 2 pi fst and sin 2 pi fst, right. So, this would be si component multiplied by some t by 2 phi s1 of t. So, if you call this entire thing as some Si, and you have similarly Sq square root of t by 2 phi S2 of t, then this would be Sq, and you can then define S of t or capture everything that is there about S of t by giving the two numbers Si and Sq, which would then allow me to construct two dimensional plane which I will call as I and Q. Okay. And in this I and Q plane, I can represent this Si and Sq as a vector. Okay. This would be my coordinate system. The coordinate system has these components of Si and Sq. So, this would be my geometric meaning of S of t. We will stop here and then we will start with the modulation methods and how do we perform these different optical modulation methods, digital optical modulation methods, and how do we represent them graphically in the next module. So, we will stop here and then we will continue in the next module. Thank you.